The operation of the AC system is a closed circuit of refrigerants such as R12 Freon, although over the years other materials have been used, notably ammonia. The Freon is pumped through the system by a compressor. The reason the system is able to cool has to do with the pressure-temperature thermodynamic properties of R12 Freon. Slide 2. To understand what is meant by the pressure-temperature thermodynamic properties of the refrigerant, I will give you some examples. It is important to understand that the pressure-temperature values shown is what is referred to as equilibrium. Equilibrium is where the material can either be a liquid or a gas. Reducing the temperature from this point will turn a gas to a liquid. Increasing the temperature from this point will turn a liquid into a gas. Starting with something we all know about, water. The following is based on the water being at sea level where the atmospheric pressure is at 14.7 psi absolute. Water at room temperature is of course, liquid. Water as we know is liquid until the temperature gets down below 32 degrees Fahrenheit, when it will change to a solid we call ice. Water will remain a solid at this point no matter how cold it gets. On the other end, water will stay a liquid until the temperature goes above 212 degrees Fahrenheit, when it will change to a gas. The gas, we call steam. This change of state can be called evaporation, or in this case boiling. On top a mountain, water will boil at a lower temperature than 212 degrees Fahrenheit, because of the atmospheric pressure is less than 14.7 psi absolute. Also why airplanes need to be pressurized as the altitude increases to the point where water can be turned into vapor. In space, which is a vacuum, water would turn to vapor. Water exactly at 212 degrees Fahrenheit and at sea level can be either a liquid or a gas. Heating water in a pot without being enclosed, will just evaporate into the air and will eventually cool down and become water again. We also know if the water is heated in a boiler, the steam will cause the pressure to rise, and as more heat is added the pressure will continue to rise. As the pressure rises, so does the temperature of the water and steam until the pressure is released. Every material has similar thermodynamic properties of solid, liquid and gas states and can be changed from state to state by either changing the temperature or changing the pressure. For example, pulling a vacuum on a container of water at room temperature will change the state of the water to a vapor. We don't think of this as steam, though, because steam is considered to be hot water vapor. On the other end of the pressure spectrum, given enough pressure the water will change to a solid even at room temperature. We don't think of this as ice, because we think of ice as being cold. To illustrate further with another material, steel will eventually become a liquid as the temperature increases. If the temperature was to increase enough it would eventually turn to a vapor. Although on Earth this would be very hard to do. Another material that is familiar is mercury, which is a liquid metal at room temperature and pressure. Slide 3. The point to remember is all materials will have the three states depending on the combination of temperature and pressure. The terms to remember are changing from a liquid to a gas is evaporation and changing from a gas to a liquid is condensing. Slide 4. Now turning to the pressure-temperature properties of R12 Freon. As you can see, the temperature of the Freon gas at 37 psig will be approximately 40 degrees Fahrenheit. And the temperature of the Freon liquid at 225 psig will be approximately 147 degrees Fahrenheit. Now that is the temperatures of the Freon, not necessarily the coils, as it takes some time for the heat to be transferred. Just like water in a pot on a stove, the fire is much hotter than 212 degrees Fahrenheit and it takes some time for the heat to transfer and get the water to boil. The graph on the right shows several common refrigerant pressure-temperature properties, with R12 and R134 being the two commonly used in vehicle systems. Notice that R12 and R134 are very similar down in the low pressure, cold region, and not very different in the high pressure, hot region. In practice, the R134 is just slightly less efficient than the R12. Slide 5. Now back to the air conditioning system. The heart of the system is the compressor. In a vehicle system using Freon, the compressor pumps the Freon through the system in a closed loop. There is really no start or end since a closed loop is a circle, but for the purpose of discussion, we will start at the compressor. At an ambient temperature of 75 degrees Fahrenheit, the system pressure will be approximately 60 to 80 psig. The low-pressure refrigerant gas is compressed to raise the pressure of the refrigerant gas up, let us say to 225 psig, and will lower the suction pressure of the compressor to somewhere like 40 psig. At this discharge pressure, the refrigerant is then sent to the condenser where air is forced over the coils to cool the refrigerant, changing the state of the refrigerant to a liquid. Refrigerant out of the condenser is next routed to a receiver dryer, which will allow the refrigerant to further condense to liquid. The receiver dryer also will contain a desiccant which will remove any water that may be in the system. There is also a filter in the receiver dryer. Out of the receiver dryer, the refrigerant flows maybe through a sight glass to the expansion valve. The sight glass, if used, is used to see if the refrigerant is completely changed to a liquid. If there is a large quantity of bubbles in the liquid, it is an indication there is not enough refrigerant in the system. In modern systems which use different refrigerants other than R12 Freon, the bubbles will not be able to be eliminated, and sight glasses have been abandoned in modern systems. When the refrigerant reaches the expansion valve, the pressure of the refrigerant is reduced at the expansion valve, which makes the refrigerant very cold and evaporate back to a gas state. To illustrate this phenomenon, if you use those compressed gas dusters, the can will get very cold as the pressure is released from the can. On my can there is this first aid recommendation. Skin, immediately wash with warm water. Treat for frostbite if necessary. The expansion valve is a temperature-operated valve that uses the temperature of the outlet of the evaporator. This will regulate the pressure reduction so as to prevent the evaporator temperature from being cold enough to cause the evaporator to form ice on the coil fins, which would reduce airflow out the vents. The expansion valve also controls the flow of refrigerant, so as to make sure all of the refrigerant is returned to a gas. This is important because any liquid entering the compressor could cause compressor failure, since liquid is not compressible like a gas is. Your brake system uses the fact that the brake fluid is not compressible to transfer the brake pedal pressure directly to the wheel cylinders or calipers. When liquid is tried to be compressed, the pressure can be unlimited and can exceed the capability of the reed valves in the compressor, and they may fail. With the refrigerant in the evaporator at the reduced pressure, the blower moving air over the coils, the air is cooled and the refrigerant temperature is raised, moving the heat from the interior into the refrigerant. This will further ensure the refrigerant is changed to a gas. The refrigerant gas out of the evaporator coils will return to the compressor inlet. After entering the compressor, the low-pressure gas will be compressed up to a pressure where the gas can again be condensed by the condenser. The heat which was introduced into the refrigerant in the evaporator will now be removed by the condenser. So in a way, a vehicle air conditioning system could be considered a heat pump. Slide 6. Since some of the older vehicles could have modern AC systems which use a capillary tube instead of an expansion valve, I will cover these briefly. The capillary tube is used to reduce the pressure the same way the expansion valve does. The difference is the capillary tube is just a very small tube, or orifice. Whereas, the expansion valve is a movable valve, that is controlled by a temperature sensor. Both will reduce the refrigerant pressure, but the capillary tube system relies on the refrigerant charge being at optimum for best performance. Too little refrigerant and the pressure will drop too low and could cause the evaporator coils to freeze up. Too much refrigerant will cause the pressure in the evaporator to be too high, reducing the cooling. Also, on modern systems there is an accumulator between the evaporator coils and the compressor. It serves the same purpose as the receiver dryer in the older system and adds the benefit of a large canister where any liquid refrigerant which remains can accumulate in the bottom of the canister rather than be returned to the compressor. This was considered important to place the accumulator here rather than use a receiver dryer after the condenser, because any liquid entering the compressor could cause compressor failure. Since liquid is not compressible like a gas is, as was covered before. Slide 7. To troubleshoot and or repair an AC system, it is necessary to have some equipment. A set of pressure gauges is a must-have. A laser temperature gun is also very handy. A can tap or charging valve will also be required. If the system needs to be opened up to replace any equipment, then a vacuum pump will also be required. And of course refrigerant and an oil charge suitable for the type refrigerant you are using. Matching the correct oil for the type refrigerant you are using is critically important. The original R12 systems used mineral oil. Most of the oil charges you can find today will be either ester or PAG oil. PAG oil is not compatible with the original systems that had the mineral oil. This is because the two oils will react with each other and turn into a gel-like substance and cause clogging and damage. It has been said that ester oil can be used with the mineral oil, but I recommend replacing as much of the original mineral oil as possible to ensure there will be no problems. At a minimum, the compressor should be drained and refilled with the ester oil. If it is possible, the hoses, condenser, and lines should be flushed to remove oil residue. Flushing the evaporator, though recommended, would be more difficult for some vehicles because the expansion valve should not be flushed. Removing the expansion valve on factory air conditioners are usually located in a pretty inaccessible spot. Most auto parts will sell a can of pressurized flush for this purpose. Most of the systems I have flushed, the stuff comes out pretty nasty. Also, anytime the system is opened up, the receiver dryer need to be replaced. One more thing, if you go to the trouble of flushing all of the system, you may as well go ahead and convert to R134 refrigerant. Slide 8. To troubleshoot the system will require the hookup of a set of gauges as shown in this slide. On the older Ford vehicles which use the type compressor as shown, has service valves on the compressor. The use of these valves is quite different than the newer vehicles that have Schrader valve type connections. The service valves have 3 different positions as shown in the slide. Notice there are not any Schrader valves in the service valves for the gauge ports. Most new gauge sets have Schrader valves in the hose connections which connect to the gauge ports. They require the Schrader valve in the gauge port to depress both Schrader valves. In order to use this type hose on the service valves, the Schrader valves in the red and blue hoses on the gauge set will need to be removed. If you convert to R134 refrigerant, there will be new quick connect adapters installed on the service valve gauge connections. The compressor isolation position of the service valves is used to allow the removal of the compressor, without the need of removing the refrigerant from the rest of the system. It also allows the oil level in the compressor to be checked. The service valves turned fully clockwise to close off the vehicle hoses, then the compressor could be removed and replaced or the oil level checked. Then the vacuum pump only needs to evacuate the compressor. When evacuated, the service valve could be opened to the center position, which allows connection to all 3 ports for pressure testing. When everything is checked out and the gauge set is to be removed, the service valve is turned fully counterclockwise to close the gauge connection port and connect the compressor to the vehicle hoses. If the system is opened up, it needs to be evacuated with a vacuum pump for 30 minutes before charging. The vacuum pump is connected with the yellow charging hose. It is recommended both the red high pressure valve and the blue low pressure valve be opened on the gauge set during evacuation. Be sure to close the red high pressure valve on the gauge set when the evacuation is finished. Slide 8.1. Testing the system. With the gauge set attached, make sure both the blue low and red high valves are closed on the gauge set. This ensures the gauges will only be measuring the pressure in the hoses connected to the service valves. Open the service valves to the service position. Both gauges should read in the range of 60 to 80 psig with an ambient of 75 degrees Fahrenheit. If little or no pressure is in the system, it indicates there is either no refrigerant or not enough refrigerant in the system. At this point, we know there has to be a leak somewhere. If the system has no pressure, the system should be evacuated before charging at a minimum. This will ensure there is no moisture in the system. You may ask, if the system is a closed system, how can moisture get in? If the compressor was run with an empty or low refrigerant condition, the suction side of the compressor can go into a vacuum, causing the entire system to be at a partial vacuum, which can pull in air through any leak that exists. After the evacuation, add enough refrigerant with a dye into the system to allow for leak testing. To do that, the valve on the refrigerant can and the blue, low, gauge set valve open. The pressure should rise to the 60 to 80 psig. Then, using an ultraviolet light, look to find out where the leak is located and repair the leak. The most common place for a leak is the compressor seals. There are also other types of leak testers which sniff for leaks. To check the pressures, make sure both service valves are set to the mid position and the two gauge set valves are closed. With the engine running with the idle set up to 1500 rpm and the AC control set to maximum and the blower on high speed, the pressure gauges should show a low pressure on the blue low pressure gauge and a high pressure on the red high pressure gauge. The pressures will vary depending on the ambient temperature and relative humidity. Higher temperatures with low humidity will result in higher pressures. I will assume an ambient temperature of 75 degrees Fahrenheit and a relative humidity of 50%. The range of the low pressure should be in the range of 15 to 45 psig and the high pressure about in the range of 75 to 250 psig. If the ambient temperature is very high, greater than 95 degrees Fahrenheit, the red high pressure can reach 300 psig, or higher. I recommend using an external fan to blow air at the condenser and radiator to keep the high pressure down. This is especially important if you have converted to R134, since it runs at slightly higher pressures. If both pressure readings are low, then the system needs more refrigerant, which can be added by opening the dispensing valve and opening the blue low pressure gauge set valve. When the system is in operation, the red, high pressure valve should never be opened. If both pressures are high, there is too much refrigerant in the system and should be removed from the system. In a shop they have special equipment to reclaim the excess refrigerant. If the high pressure is normal or very high, and the low pressure is low, it would indicate a restriction between the compressor discharge and the evaporator, or a restriction between the evaporator and the compressor suction. The usual suspect is the expansion valve being stuck closed or clogged with ice. To check for ice clogging due to moisture being in the system, shut down the system to allow the expansion valve to warm to ambient temperature. This can be sped up with a hair dryer blowing on the expansion valve. Start the system back up, and if the pressures return to normal and the evaporator is now cold, there was excessive moisture in the system and the system should be evacuated again to remove the moisture. Anytime the system has been opened 3 times, I would recommend replacing the receiver dryer. Generally they are not that expensive and worth the insurance to prevent expansion valve internal icing. Other possible issues could be a plugged up condenser tube, unlikely, or a plugged up receiver dryer. Also, the receiver dryers are filled with a bag of desiccant which can rupture and let the desiccant find its way to the expansion valve. There can be some other spots in the system, like the sight glass, if equipped, that can collect desiccant. I would recommend replacing the receiver dryer on any vehicle that has not had the AC system in use for several years. If there is a restriction indicated, one way to isolate where the restriction is located is to use the temperature gun to look for a temperature drop in the lines. Any restriction will cause a pressure drop and thus a corresponding temperature drop. If the low pressure is high and the high pressure is normal, it is an indication the expansion valve is stuck open. This condition could cause the refrigerant to not be completely turned to a gas in the evaporator, and the compressor can receive slugs of liquid refrigerant. Slugs of refrigerant liquid will make the compressor very noisy, making a rod knock type sound. Also, the suction line will be colder than normal and may frost up. If the two pressures are equal or near equal, say within 20 to 30 psig of each other, it is an indication of compressor failure. A healthy compressor will have a discharge pressure about 6 to 7 times the suction pressure. Slide 9. Inside the compressor are reed valves. The suction reed valve will open when the piston in the compressor is pulled down to let the refrigerant from the evaporator fill the cylinder. When the piston is pushed up, the refrigerant is forced out through the discharge reed valve. Since the volume of the compressor stroke is larger than what the expansion valve will allow through, the pressure will build up until there is enough pressure at the inlet of the expansion valve is enough to let the compressor volume through. If you hear your compressor knocking or making excessive noise, it may be due to either a loose belt or excessive discharge pressure causing the suction and the discharge reed valves to violently slap closed. Also, if liquid refrigerant is sucked into the compressor, it will knock. Slide 10. This slide shows the common issues that air conditioning systems have. Insufficient or no cooling. 1. Inoperative magnetic clutch. 2. Inoperative blower motor or switch. 3. Obstructed air passages. 4. Complete loss of refrigerant charge. 5. Partial loss of charge. 6. Service valves improperly set. Should be maximum counterclockwise. 7. Inoperative heat to AC door in the evaporator, heater box. 8. Compressor defective, or loose, or broken drive belt. 9. Temperature control defective. 10. Magnetic clutch lead disconnected or broken. 11. Expansion valve defective. Stays open or closed. 12. Moisture in system. Noisy compressor. 1. Loose, torn, or misaligned drive belt. 2. Loose clutch. 3. Foreign material or damaged compressor. 4. Compressor mounting loose or support rods missing. Compressor vibration. 1. Broken or loose compressor mounting brackets, or compressor brace. 2. Loose clutch. 3. Loose belt.